Hi everyone. So the last class we talked about functions known as Mobius transformations, which were defined like this to be the ratio of two linear functions. And we realized that we needed this condition that AD minus BC was not equal to 0, so that f wouldn't be a constant function. Otherwise it's a constant function. And kind of the punchline of class yesterday was that this function gives a bijection from its domain, which is all of the complex numbers except for the point negative d over c, because if we plug that in, we'll be dividing by 0. So that's the domain of the function, and the point is it's injective on this domain, and it maps to all of the complex numbers except for one particular point, which is a over c. So it's a bijection from the complex numbers minus a point to the complex numbers minus a different point. And furthermore, it's easy to check using rules of derivatives that this function is holomorphic on its domain. So it's a pretty nice class of functions for different choices of a, b, c, and d. And I guess the other thing we saw yesterday was that the function's invertible, and its inverse is also a Mobius transformation. So these are pretty nice functions. And today we're going to continue studying them, and it turns out that we can say even more about them if we talk about infinity. Infinity is not a number, as you know, and as with many things, it's a little more complicated in the land of complex numbers than in the land of real numbers. And that's basically because if we're on the complex plane, there's many ways that we can go off to infinity, right? There's many paths to approach infinity, just like with complex numbers, there's many different paths to approach any complex number. But again, like I said, infinity is not a number. So where it's going to come up is when we're talking about limits. And basically, it's just a way of talking about something being unbounded. So let's say we're looking at a limit of some function as z approaches some z naught. We're going to say that this limit is infinite. It's infinity if, so intuitively, first I'll say sort of the intuition behind it. Basically, if the modulus, so the size of f of z, gets arbitrarily large. So I don't really care if f of z is positive or negative or whatever its argument is, if it's I times something. All I care about is its size. And if its size is getting larger and larger as z goes to z naught, then the limit of f of z as z goes to z naught will say that that's equal to infinity. But of course, there's a precise definition. So more precisely, the limit's equal to infinity as we approach some z naught if, and it's an epsilon delta definition. So basically we want to encode the fact that f of z is getting arbitrarily large. So we say for any m greater than 0, and I use m instead of epsilon to remind myself that I'm thinking of m as a really big number, whereas usually epsilon is denoting a small number. So for any large m, real number greater than 0, I can find a delta usually delta is small, so that whenever z minus z naught is less than delta, so whenever z is really close to z naught but not equal to it, so whenever the modulus z minus z naught is less than delta but greater than 0, then the modulus of f of z is larger than m. Okay, and so this is saying that no matter how big an m I choose, if I get close enough to z naught, then the size of f of z is going to be bigger than that m. And if that's the case, we say that f of z is approaching infinity. And again, we're just looking at the modulus of f of z, so we're not caring about the argument of this complex number. So for example, some functions who have a limit equal to infinity, so 1 over z, as you might imagine, as z goes to 0, this limit is infinity. Another one is negative 1 over z. As z goes to 0, the size of this is also getting larger and larger. So this is also infinity. And another example could be, for instance, negative 1 over the modulus of z. So this is always a negative number, but its size is getting larger and larger as z gets closer to 0. So this limit's also infinity. So those are just some examples. Okay, so that's one new limit definition involving infinity. The other is we want to talk about the limit as z approaches infinity. So we say the limit as z goes to infinity of f of z is equal to some function L. So again, intuitively, this means that as the size of z gets larger, f of z gets closer and closer to L, i.e., so now the formal definition, for any epsilon greater than 0, so we're wanting f of z to get really close to L, so we're going to use an epsilon to sort of bound the distance between f of z and L. We basically want to say that as long as the modulus of z is sufficiently large, f of z will be really close to L. So the way we say that is we can find a large value of m. So there exists a positive real number m greater than 0, so that whenever the modulus of z is greater than m, f of z is within a distance of epsilon from L. Okay, so this is saying that as z gets larger and larger, f of z gets closer to L. And again, let me just emphasize that we're looking at all different paths of z so that the modulus is getting larger and larger. And so we can go in lots of different directions, and in all these directions, f of z has to still be approaching the same number L. So these are all paths that z can take to infinity. So I'm never going to talk about minus infinity because we've got so many different directions. We're going to think of all of them as infinity. Really, again, what we care about is that the modulus is getting large. If the modulus is getting large, then we say z is going off to infinity. So there's no such thing as minus infinity in this context. Okay, and then there's a third definition. We can talk about the limit of a function as z goes to infinity. We can talk about when this limit is equal to infinity, and I'll leave this definition as an exercise. See if you can guess what it should be based on definitions A and B, and then go read the textbook and check. Okay, so infinity is just a notion that's useful for defining limits, but it turns out to be kind of a good idea to think of it as an extra point that we're kind of adding to the complex plane. If we want to do this formally, we can introduce it's called the extended complex plane. And we'll denote it by C hat, C with a hat on top. And what is this? Well, so it's a set, and the set includes all the complex numbers and a new point, which we're labeling infinity. So it's just a way of talking about the complex numbers plus the number infinity. It's a complex plane with one extra point. And I want to emphasize that infinity is not a number, so we can't do normal arithmetic with it. But we can define some operations as if it were a normal number. So for instance, if a is a complex number, so if a is in C, we can define the following. So I'll define infinity plus a to be equal to infinity. If I add a finite number to infinity, I get infinity. Similarly, infinity times a is equal to infinity for any complex number, except for 0. So infinity times 0 is not defined. And this is one reason why infinity is not, we can't think of it as a number, is because we can't define arithmetic for all complex numbers. But infinity times a non-zero number makes sense. It's just infinity. Similarly, infinity times infinity makes sense. That's also going to be infinity. If I have a complex number a and I divide by infinity, you can guess what we should get. This has sort of infinitely large size. This has finite size, so the ratio should be size 0. But again, this is only if a is non-zero. So 0 divided by infinity. No, sorry, that's okay. 0 divided by infinity, of course, that should still be 0. The other one is a divided by 0, so that's equal to infinity, but only if a is non-zero. As we know, 0 divided by 0 is not defined. Okay, and if I define arithmetic this way, then the usual rules of limits work with infinity also. So for example, let's say I have the limit as z goes to z naught of f of z is equal to some a, and the limit of some other function g of z as z goes to z naught is equal to infinity. Then the limit of the sum as z goes to z naught, if a is a complex number, this is going to be equal to the sum of the limits. Well, you can check using, you can prove this yourself that this equals infinity. And then we say that that's equal to the sum of the limits because we defined a plus infinity to be infinity right here. And so, multiplying functions, adding functions, dividing functions, the usual rules of limits will apply with infinity limits as well if we follow these conventions. Okay, and so that's why it's useful to introduce the extended complex plane with this extra point, which appears sometimes as a limit. One warning is, you might think infinity plus infinity is okay, but it's not. This is not well defined. And what I mean by that is I can have a function f whose limit is infinity, a function g whose limit is infinity, but the limit of the sum of those two functions may not be well defined. And so there's no way to make sense of this. For instance, well, the book has an example. So like, let f of z equal z, g of z equal minus z, then the limit of f as z goes to infinity is infinity. Limit of g as z goes to infinity is also infinity, right? Because all we care about is the modulus, right? But if you look at the limit of f of z plus g of z as z goes to infinity, that's 0. Why? Well, because f plus g is just 0. So it's a constant function in parentheses here. And so examples like this show you that there's no way to make sense of infinity plus infinity in a way which still obeys the limit rules that we want. Okay. So we've got this set, c hat, which is the complex numbers plus this point at infinity. And what I want to talk about now is how to visualize it. Because there's a really nice picture of what the extended complex plane looks like. It requires kind of folding the complex plane up. So I'll tell you what I mean. So first, how do we visualize the complex plane? Well, it's a plane. So I can't draw all of it because it's infinite, but I'll draw part of it. Here's the complex plane. Here's the origin, 0. And what I'm going to do is I'm going to set a sphere on top of it, like that. So this is a three-dimensional, it's a hollow sphere, so think of it as like an inflatable ball or something. I'm going to set it right on top of the origin. So I've got the sphere, which I'll call S. And I want to identify points on S with points in the complex plane. And the way I do that is what's called stereographic projection. Literally, I'm going to pretend I have a light source, and I'm going to project points on the sphere down to points on the plane. So the way I do this is basically pretend you have a laser pointer, and you position it right at the North Pole. So here's the North Pole, N, and you shine a laser through the North Pole. So at first, this laser is inside this hollow sphere because it's going in through the North Pole. Maybe I can try to draw that. So let me fix my picture here. So it's inside the sphere, but then at some point it hits the other side and it comes out. Maybe it comes out at a point X here. And then the laser continues. Say the sphere is a little translucent, kind of like in our picture. And at some point it hits the complex plane. And so I'll call this new point, which is on the complex plane, I'll call that pi of x. And so I'm thinking of this projection, this laser pointer, as defining a map from the sphere onto the complex plane, which sends the point x to pi of x. So pi is a function from the sphere S to the complex plane. However, it doesn't map every point of the sphere onto the complex plane. Why? Because there's nowhere for the North Pole itself to go. So really it sends not the whole sphere, but just the sphere without the North Pole. So if I remove the North Pole from the sphere, then I have a well-defined map, which I'm calling pi, which goes from the sphere without the North Pole to C. And this is a bijection. For every point on the sphere minus the North Pole, there's a unique point that it gets sent to on the complex plane, and this map hits every point of the complex plane just by moving my laser pointer around. Okay, and so this allows us to identify the complex plane C with points on the sphere, right? And now what you see is, notice that if x gets closer and closer to the North Pole, so if I move x up to the North Pole, then I'm basically, to make my laser go through that new point, I have to rotate it down. So here's some new point. Maybe I'll call it x prime. And this map pi sends x prime to somewhere kind of farther out on the complex plane. And if you think about it, actually, the arguments of pi of x and pi of x prime are going to be the same, but the modulus of pi of x prime is larger. And so as the point x gets closer and closer to the North Pole n, the size of pi of x gets larger and larger. In other words, another way to say it is that pi of x goes to infinity. So its modulus is getting larger. And so this extra point at infinity, we can think of it as corresponding to the North Pole, because if we take a sequence of points in the complex plane that are going off towards infinity in some direction, then if I identify all these points with points on the plane, or sorry, points on the sphere, those points on the sphere are getting closer and closer to the North Pole. So we can identify infinity, this point inside the extended complex plane, with the North Pole on the sphere. In other words, there is a bijection between the points of the extended complex plane and all the points of the sphere. Because previously we're just missing the North Pole, but we see, oh, the North Pole actually just corresponds to this extra point at infinity. And so the way to visualize this identification is you're kind of taking the complex plane and you're like wrapping it up onto this sphere, and you can wrap all of the complex plane onto the sphere, and then the point at infinity would end up at the North Pole. And this is a good way to think about these limits, is to think about the extended complex plane actually is this sphere. So that's how we're going to visualize it. So this is actually the beginning of a really interesting story that if you go on to graduate mathematics, you'll explore more. But this sphere is called the Riemann sphere, or the complex projective plane, CP1. we'll, in our class, we'll probably just keep calling it the extended complex plane, C hat. But if you ever see these words, you actually know what they are. It's the complex plane together with this point at infinity identified with a sphere. Okay. So that was a little bit of a digression. Let's go back to Mobius transformations. So let me just write out a general Mobius transformation here. So exercise for you to check is that we have the following limits. If I look at the limit of f of z, so where is this function not defined? Remember, it's not defined at negative d over c. But if I look at the limit as z approaches negative d over c, you'll see what's happening is this denominator gets larger and larger, and so the modulus of f of z is getting, the denominator is getting smaller and smaller. It's getting closer to 0, and so the modulus of f of z is getting larger and larger, and so this limit is equal to infinity. And you should check this by hand using the official definition of this limit. And then similarly, we can look at the limit as z goes to infinity of f of z. And in fact, you'll see that it's equal to a over c. You can prove this using the epsilon delta definition of the limit. But if you believe that the rules of limits hold when we involve infinity as well, then it's kind of easy to see, because the limit of f of z, well, let me write out what it is. So az plus b over cz plus d. So I'm looking at as z gets larger and larger, so I can assume that z is non-zero, and so I can multiply by 1 in a clever way. I'm just going to multiply both the top and the bottom by 1 over z. Since I do that to the numerator and the denominator, I'm not really changing the expression. And so on the numerator, I get a plus b over z over c plus d over z. And I'm letting z go to infinity. This is the limit of a ratio of two functions. And so as long as as long as the denominator is not approaching 0 as z goes to infinity, which is not, it's not, I can rewrite this as the ratio of the limits. But what's happening here? Well, b is a constant, so b over z, as the modulus of z gets really large, the modulus of b over z gets really small. So this expression I've circled goes to 0. And similarly with d over z, and so we just get a over c. Okay, and so what this means, remember, the function f, negative d over c wasn't in the domain, and a over c wasn't in the image of this function. But this is saying if we also allow the point infinity, so if we think of this function on the extended complex plane, then we can also talk about these 2 points. So let me be a little more precise. So I'm going to define a function. I'm going to call it f hat of z. I don't think this is what the book uses, but that's okay. So f hat's going to be a function from the extended complex plane to the extended complex plane. I'm going to involve infinity also. And I'm going to define it to be just the usual Mobius transformation. If z is not equal to negative d over c or infinity. I'm going to define it to be infinity if z is equal to minus d over c. And I'm going to define it to be a over c if z equals infinity. And so I'm kind of filling in the holes where my original Mobius transformation wasn't defined. And then it turns out that f hat is a bijection from the extended complex plane to the extended complex plane. So another way to say it is f hat gives a function which moves all the points on the sphere to other points on the sphere if I identify the sphere with the extended complex plane. And also, the fact that we have these limits here also tells you that it's a continuous function. Now, I haven't defined what continuous means for functions on the extended complex plane, but I'll leave that to you to think about. So this is a good way of thinking about Mobius transformations, is we fill in the holes with these definitions, and we get a bijection on the complex numbers as long as we add these infinity points.